So today we are going to study about heat and how heat is transferred in different material. So heat can be transferred either through conduction or convection or through radiation. So by conduction in a solid material, if one part of the solid is heated and is at a higher temperature and the other is at a lower temperature, then heat will flow from um, one point to the other. And some of the examples of good conductors are metals, diamond, while bad conductors of heat are wood, glass, etc. While when we're talking about convection, then it means that the heat flows in a fluid. We're talking about a fluid. So let us say that if we have a water body and it is being heated, then the hot molecules will rise up and the colder ones will come down, and so this heat transfer will take place. Similarly, if due to sun, the atmosphere of earth gets heated up, so the hotter air molecules, they get lighter and they go to the upper part of the atmosphere, while the colder air molecules, they come down. So this kind of movement of the air molecules will take place. While by radiation, let's say we are talking about sun and earth. So the photons from sun will reach earth and earth gets heated up, and at night it radiates IR rays and it loses its energy. And all the hot objects will radiate heat. So radiation by radiation. So let us say that if we talk about iron, and if it is red hot, it will emit IR light, and if it is white hot, then it will emit all the wavelengths of white light spectra. As we discussed that heat can be conducted by conduction, convection, and radiation. In case of conduction, the heat is transferred through lattice vibrations. Now, before starting that, we know that the electromagnetic radiation is quantized, and it is given by, and it depends upon the frequency and multiplied by a constant number h. Similarly, lattice vibrations are also quantized. So you see that all the atoms in a lattice, they stay together in a lattice, and we assume that they are tied together by some linear springs. The amount of heat, the energy associated with this kind of a system is actually given by Hfn. So where Fn is the natural frequency of the oscillator. So in case of a conductor, you see that heat can be conducted if suppose the material is a crystalline material, then if we are assuming that it is all the atoms are attached together by springs, then if heat is on one side of the material, then one of the atoms or one side of the atoms, here we have taken two-dimensional material, but it can be it will in actual be three-dimensional material. So these atoms, if when they absorb heat, they start oscillating with higher amplitudes. But as these atoms are associated and attached to other atoms as well, so you see that because of this coupling with other atoms, they will also start oscillating. So if one atom is oscillating, the other atoms will also oscillate in accordance with the oscillation of the first atom. So and the transfer of heat will take place from one point to the other. And such a situation can be very easily seen in metals, where you see that the heating of the metal takes place very easily when it is heated. While if you take an example of an amorphous material, for example a plastic, you see that these chains of atoms, they are very haphazard, and therefore heat will not be able to reach from one point to the other. If suppose the source of heat is here, then if suppose that we are talking about this chain, then the heat, if this atom starts oscillating with larger oscillation amplitudes, it will transfer this amplitude vibration to the other atom, and then to the next, and then to the next. And you see that the transfer of heat from one point to the other will not be very easy. That is why you see that in household pots and pans, the pots are made up of metal, and usually the handles are made up of plastic. So the rate at which this energy transfers from one point to the other depends upon the thermal conductivity, which is Kc. So if faster heat conduction will take place, then the material will have higher thermal conductivity. And if it is slower, we say that the material will have lower thermal conductivity. So now we were discussing about different kind of heat conduction quantas or mediums that are present, or carriers that are present, heat carriers. So you see that in insulators and in semiconductors, most of the heat is conducted by phonons, which are the primary source of conductors of heat. While in metals, the primary source of primary conductors are electrons, while there will also be some conduction by phonons. So as we have discussed already, that in solid material, all the atoms, in a crystalline solid material, all the atoms are attached together by linear springs, and if one atom starts oscillating, the oscillation will be transferred to the other atoms as well. So let us say that we are taking this linear chain here, which has only 3 atoms, and let us say the heat is provided from here. So this atom starts oscillating with the higher amplitude, so the spring attached to it will be affected, and after some time this atom will start vibrating, and this contraction of the spring will be shifted to the other side of the lattice. Here it is a one-dimensional lattice. Similarly, at a later time, this heat will leave the system, and therefore the system will get back to its equilibrium position. Okay, so we have known that the energy associated with a spring mass system or a harmonic oscillator is quantized, and it is given by n plus half hfn. So that is why these phonons, the vibration of atoms creates a wave, and the quanta of that wave is known as a phonon. And those phonons will have these definite energies, definite fixed energies, and they are quantized energies. In the part 1 of this, we have found out that this energy actually is a sinusoidal function. And from here we can find that, so this is the dispersion relation for a phonon, for a one-dimensional lattice. So if we draw this, it comes out to be something like this. And we see that the maximum of this frequency comes out to be at plus minus pi upon a. And when we equate, find out the maximum of this frequency, we find that will give us the minimum wavelength that will be present. So the minimum wavelength that will be present will be actually 2a. So let's understand it better. Okay, so suppose that this is the chain of atoms we are talking about. So the maximum wavelength will be, suppose the length of the crystal is L. So the maximum wavelength will be n lambda upon 2. So just like in standing waves, you see that if you have a string like this, so this will be the maximum wavelength that will be possible. Similarly here as well, it will depend upon the length of the material. While in the string it depends upon the length of the string. So if this is the length of the string, and it will be n lambda upon 2. From here you can find out the maximum wavelength, that will be 2l upon n. Similarly, the minimum wavelength, as we have calculated, will be given by 2a. So there will be no other wavelength except for some wavelengths in between these two. So it cannot be lower than this, and it will always be quantized. So you see that in a one-dimensional lattice, and if it is a monoatomic lattice, you only have acoustic phonons that will be present, because of which we got a dispersion relation, which was something like this. Now this dispersion relation actually is symmetric and periodic. So usually you'll see that only half of this dispersion relation is plotted. So you sometimes you'll see that only this part of the dispersion relation will be available. And this is for the acoustic phonons, because in a one-dimensional lattice we only have acoustic phonons. While in a diatomic lattice, you see that there will be some additional degrees of vibrational freedom and phonon frequencies that will be available. So that is why we'll have different energies of phonons that will be present. So there will be some low frequency phonons and some high frequency phonons. High frequency phonons are called optical phonons and low frequency phonons are called acoustic phonons. So optical phonons just means that the phonons, they will be able to absorb electromagnetic waves, and they will be actually oscillating with the energy of an electromagnetic wave, while sound waves are low energy waves. And so the low energy phonons, they are also called acoustic phonons. So let us take an example of a NaCl crystal and just take a one-dimensional linear chain of this crystal, and if all the ions vibrate in phase, it will be a higher wavelength wave, which will be acoustic mode of the phonon will be present, while if the ions vibrate out of phase with each other, so it means that the chloride ions or sodium ions, they are out of phase with each other, so the wavelength of such linear chain will be smaller as compared to the acoustic mode, where the ions are vibrating in phase with each other. That is why it will be a low energy mode and this will be a high energy mode. So in the dispersion relation also, you will have some low energy phonons, dispersion relation for low energy phonons and for high energy phonons. But this is for a one-dimensional chain. But if it is a two-dimensional chain or a three-dimensional lattice, then the dispersion will be something like this. So it will have acoustic mode and it will have optic phonons and acoustic phonons. So optical phonons can be of two types, transverse optical phonons and longitudinal optical phonons. Also the acoustic phonons can also be longitudinal acoustic phonons and transverse acoustic phonons, because of the more number of dimensions that are available for the ions to vibrate. Now this can also be compared with the dispersion relation for electron, just to give you a better understanding, which you might be familiar with this kind of a band structure. So if we draw only this part of the energy versus K spectra, so we see that if it is a direct band gap, so it will look something like this. So this we can also draw for a silicon electrons, and you'll see that because silicon is the indirect material, so the minima of the conduction band and maxima of the valence band, they are separated and they are not at the same K value. And one more thing that is to be observed here is that the energy of phonons is much less as compared to the energy of electrons. This is because the mass of electrons is very less as compared to the mass of the ions.